Hi everyone, welcome to Linear Model with Miss Harini Abdullah. In this video, we still be learning about the logistic regression. So in the previous videos, we already discussed about having a binary response instead of ratio scale response for our regression model. And we also discussed how to find a proper link function to connect that response variable with the predictors in the form of a linear multiple model. And we end up with the logit link function. And we also already learned how to find an equivalent form of the model, of the logistic model, because in some cases, probably we just want to have a direct use of the model, for example, to calculate the probability of getting into a success category instead of just calculating the logarithm of the odds. And for this session, in this video, we will learn about how to do the interpretation of the regression coefficient for the logistic model. So, again, let's just recall the form, the linear form of a logistic regression model given by the logarithm of the odds is a linear combination of the predictor variables that we have in here. And then let's say we want to evaluate the contribution of X1 in, explaining whether an observation will get into a success category or into the other category. So in that case, just following the standard procedure that we have in a linear model, we just need to set the value of x1 to a certain value, and then we change its value by 1 unit, keeping all other covariates constant. So in this case, let's set x1 equals a, and we substitute this into the model. So we have that the logarithm of the odds, and then we give subscript 1 in here to represent that x1 equals a is the first condition that we consider. So in here we have beta naught plus beta 1 times a plus blah 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 plus beta p x p. And then let's just increase the value of x1 by 1 unit. So we set x1 equals a plus 1. So we calculate the logarithm of the odds for the second condition here, represented by the subscript 2 in here. So then substitute this value into the equation. So we have beta naught plus beta 1, a plus 1, and blah, blah, blah. All other variables, we don't change the value of them because we just want to assess the contribution of x1. So then we calculate the difference in the value of log odds of these two conditions. So beta naught, they cancel out. Beta 1 also cancel out. All the way to beta p cancel out. What's left is just this one. Beta 1 times 1. That is by subtracting the first equation from the second equation that we have in here. So we have the difference in the logarithm of odds is just beta 1. And applying the property of a logarithm function, difference in logarithm is just the logarithm of the ratio of those two odds. So we have logarithm of odds 2 over odds 1 is given by beta 1. And then we don't like having logarithm function here. So how to cancel it? We just take the exponential. So then we have odds 2 over odds 1 is given by e to the power of beta 1. And the ratio of odds here, we know it is very well known as the OR. It stands for the odds ratio. So here we can see that, okay, so odds 2 is odds 1 times e to the power of beta 1. So this is how we do the interpretation of the of the regression coefficient in a logistic regression. That is, instead of saying that, okay, beta 1 is the change, the increment if beta 1 is positive, or the decrement if beta 1 is negative. So we just say the change in the value of logarithm of odds when x1 is increased by 1 unit. That statement is mathematically correct, but it's really difficult to imagine is it a big change or a small change, or what does it mean, the change in the value of the logarithm of the odds? It's just too much to be able to visualize or to imagine what actually it represents. So we don't really do that. And from this process, instead of interpreting beta 1, it's much more meaningful if we do the interpretation of the exponential of the beta 1. So we can say that the odds of the changed condition is e to the beta 1 times the odds from the first condition. So we can see here that this is much more interpretable, because we can say if the odds is higher, it means that the likelihood to be successful or to get in a success category is higher as well, because in here the odds is the ratio of probability of being success over the probability of being not success. Okay, or we can also measure actually the change, or this is just saying, okay, the odds is multiplied by this much. So how much is the difference? How much is the change? We can just do, okay, then we can just have odds 2 minus odds 1 over odds 1. I mean that this is the relative change, right? So we can have e to the power of beta 1 of odds 1 minus odds 1 over odds 1. And then we have here e to the power of beta 1 minus 1 times on odds 1 over odds 1 times 100%. If we want to, if we want to do the interpretation in the percentage, so we have here something like this. So if we want to say the increment or the decrement in the odds, we can say it, okay, the odds is increased by e to the power of beta 1 minus 1 times 100%. Or if you want to just tell the story about the end condition, then we can say, oh, now the odds is e to the power of beta 1 times the odds, the initial odds. So, to sum up, we can say that a binary logistic regression is used to model a binary response variable using the logistic function. And e to the power of beta j is the multiplier of the odds of success when xj is increased by 1 unit.